Alright, so welcome to another AQA A-Level Chemistry video. This is a continuation, or I should say, the part 2 to the previous video, which was on rate equations. I'll leave a link in the description to that last video on the part 1 for rate equations. I'm now going to be starting the part 2, where I'll be talking about rate determining steps. I'll give a couple of analogies to rate determining steps. I do believe that is the majority of it. It's mostly talking about rate determining steps and how that's related to rate equations, and why it's important to understand the rate determining step. And at the end, I've got an example because I wasn't really happy with. I wouldn't say I wasn't happy with, but I think I could have done better examples compared to previous example that I gave. Because there's more. There's quite a basic understanding of a question, and even the question that I'll give you is an AQA A-Level Chemistry question, but I feel like it's harder than the one I have here. I say harder than, it's just a bit more realistic, I should say, to the real exam. It requires you to have good understanding of orders, but it's not too difficult to the point where you'll really struggle. I think the next time when I get to, as I said before, when I finish all of physical chemistry, I'll be doing all the exam questions from AQA for all of physical chemistry, and I'll get questions that are a bit harder, but at least they'll be more. It'll better prepare you. The question I'll ask you at the end is not too difficult, because I wanted you to get the hang of this. But I think you should be trying to answer harder questions, in my opinion. But anyway, I'll go straight. I'll stop talking. Get straight into the video. So, rate equation. So, the rate determining steps. Reactions don't always happen in one step. They may need many different collisions. Fortunately, most reactions have one step much slower than the rest, and so rate equation only depends on this one step. The RDS, or the rate determining step, is the slowest step in a reaction. It's the slowest because it has the highest activation energy for a successful collision. So I'm not gonna go too much into. I'll go into the analogy first of all, just for your understanding of what a rate determining step is. It said it there. It's just a slow. If you have a multi-step reaction, there'll be one. Usually there'll be one. For AQA, at least, I'm not gonna go too much in detail about higher understanding, but there's usually one step that's much slower compared to all the other steps. So, for example, if thinking about a mechanism for example, in organic chemistry, there's multiple steps. There may be one step that's much slower compared to the other steps, and that's because it requires the highest activation, and because it has the highest activation energy, so it requires more energy for that reaction to happen. Hence, why it's a much slower step, and because it's the slowest step out of all of the different steps, the rate of the reaction is dependent on how fast that step is allowed to happen. Hopefully that makes sense. Now I've got an example here. I've got like I won't say example, an analogy for you to understand, right? So think of a commute to school where you're taking, this is one that I just made up. So think of a commute to school where you're taking a bus to a train station, right? So if you're in the morning and you're the type of person that needs to take a bus to get to the train station, but you know that in the morning, generally most roads are quiet, apart from maybe one main road that leads to a T junction where there's a traffic light that takes a long time to turn green. I use this example because, for example, vehicles that are way before that main road and vehicles that have already passed the traffic light on the main road are able to move much more quickly, but it takes what feels like forever, right, to wait at the main road where traffic has started to build up and the road has become congested because you're waiting for the slow traffic light to turn green so you can continue to pass and move on with your journey. So getting past the traffic light on the main road would be like the rate determining step in this example, because the commute in this example would represent the reaction overall, is determined, so I shouldn't say us determined, is determined by how long slash quickly it takes for you to get past this road. All right, one second, I'm going to show you, let me actually get a sketch out. There we go. Because I think some people may not be able to understand what I'm trying to say. So let's say the train station is here. So we're starting at point A. Oh, let me change this to A. This is point A, and train station here is point B. You're trying to get here. Now, generally in the morning, let's say the path is like this. and then there's a little side road here, and then this, right? I know there's many different routes that bus can take, right? But like, so there's many different buses that can go different routes. But say this is your general commute, right? And you'll say generally, for the majority of time, getting from here to here doesn't take that long. Like generally, there's not many buses, there's not many vehicles on the road here. The bus actually quite moves quite quickly when it's moving along this road here, right? And the bus usually moves very quickly along this road here, right? But let's say for example this road in particular moves quite slowly because there's a traffic light that's quite slow, or it's very slow to turn green. So generally your route is actually quite fast from here and here, right, where it's red. But this green road here, this road here, is usually the slowest road, and it's the one that can determine whether or not you're going to get to the train on time, because this road is the slowest. So this road here, so basically what I'm trying to say here is your route is mainly determined by how fast you're able to pass by this road. You don't really care too much about this road here or this road here. I use a different color, so I won't use that color. Your route isn't determined by how fast you're able to pass through this road here and this road here, because in general the bus doesn't take that long to get from here. Like, or when I say it doesn't take too long, it may obviously this road here is longer than this road, but there's not much traffic that's passing by here. There's not much traffic that's passing by here. Like, you don't struggle to get past this road. That's not your main concern. Your main concern is, if I take the bus, is this road going to be heavily congested? Is it going to take a lot of time to get past this road? Because usually that's where there's a lot of congestion, it's a very small road, but this road is fundamental and determines whether or not I'm able to pass by this road, right? So it's fundamental in determining how quickly I'm able to get to my destination, or how quickly I can pass by the road to continue on my journey. Now think of this little step here as being the rate determining step, right? So think of A to B. So think of this whole thing of A to B as being the entire reaction. So going from A to B is the entire reaction. So this is one step. Think of A to, let's call this, let's call that part, let's call this junction here, junction alpha, right? And let's call this junction here, junction beta. I'm going to use probably a different color for them. Right? So to get from A to alpha is usually, doesn't require a lot of energy. So it's low energy. So let's say this is a 3-part reaction, a multi-step reaction. So to get from A to B, you have to go from A. So you can think of it like a Hess cycle, I guess, in some sort of way. What I think about it like that? Let's not do that. Let's not make it too complicated. A to alpha. To get from A to B, you have to go from A to alpha, alpha to beta, to beta, and then from beta to B, right? I'm saying that from A to alpha is generally low activation energy. So the activation energy for this reaction from A to alpha, so from A to alpha, the activation energy is low. I'm calling this road A to alpha. From that's what this road here represents. Sorry, I forgot to use a different color. That's what this road here represents. And then to go from beta to B is also low energy reaction. Oh, forgot about that. But to get in between those two roads, there's alpha to beta. Now, alpha to beta, we'd consider that a high activation energy, right? I say high activation energy, like because of roads. I'm not talking about roads. I use the roads. I use the journey like an example for this analogy, right? But what I'm talking about here is let's not talk about the activation energy here. Let's talk. I want to continue with my analogy when I'm talking about a road, right? I'm going to continue about my analogy of the road. I don't want to. I don't want to. I want to get people this analogy first, so then I can relate it back to the to uh to the actual reaction. So let's say A to alpha, low stress. It's a low stress road. It doesn't require a lot of stress. There's not many cars coming. It's not gonna it's not a difficult road to pass by. Right? It's not detrimental to your journey. So low stress road. But to get from alpha to beta, a lot of stress, because it's like you it takes quite a long time just to get from alpha to beta. See, high stress. But then to get from beta, once you've passed by that road, beta to B, which is the train station, getting from after the light road for going to the train station, is low stress again. It's not that much stress. And now that I've finished my analogy, all these things here relate to a road. So let's relate to a reaction. So this is, say this is a three-part reaction, as I said before. If I'm going from reaction A to alpha, that would think, instead of saying low stress, it's now a low activation energy reaction, right? Sorry, I made this video kind of like with too much. I should have been a bit more concise with this, but when I mean low stress, we were using this as an example of a road, but think about this like a reaction, because that's what I'm trying to talk about here. To go from A to alpha, it is a low activation energy. It doesn't require a lot of energy to do that first step from A to alpha, but from alpha to beta, that step requires a lot of energy, and therefore it's the slowest reaction because it requires the most energy. So the activation energy for this reaction is has a high activation energy to do that step of the reaction. As I said, this is a three-part reaction. So the first part is low activation energy. Second part is a high activation energy, and this last step after it's done, alpha to beta, beta to B it goes back down again to having a low activation energy. And that's the complete reaction. The rate determining step, hopefully you understand what I mean. Hopefully you should see what I mean here. The rate determining step is this alpha to beta, or what had circled in green, from alpha to beta, because that reaction has the highest activation energy, it's the slowest reaction, and because it's the slowest reaction due to its high activation energy, the reaction rate is determined by how fast the rate determining step is allowed to happen, i.e., the rate of the reaction is determined by how fast really it gets from alpha to beta. But we consider A to alpha as being negligible, and B to beta as beta to B being negligible, because those reaction rates happen quite fast because they have low activation energies. Obviously, when you go to higher level, you consider those, but the rate determining step is the one that has the biggest influence on the rate of this reaction, and that's why we call it the rate determining step, because this step determines the rate of the reaction. All right, hopefully you got that analogy. I'll go back now and just continue the rest of my video. And that's what this is what this whole paragraph was me explaining. But I think me just saying it out loud was kind of difficult for you to understand. I thought maybe me drawing out what I meant would make a better example of what I was trying to say to you. But anyway, I'll continue on. Hopefully that was helpful. If it wasn't, and you think I could have done better, leave a comment. If you did like it, tell me in the comments, and I will just keep going. Some mechanical information. The rate equation for a reaction can give us some important details about the mechanism for the reaction. So rate determining step and the reaction mechanism. Any reactant appearing in the rate equation is involved in the rate determining step. If two reactants appear in the rate equation, we know they're both involved in the rate determining step. This means the mechanism must involve them colliding at some point. All right, so what this means is, I'll go back down to, so go back down to this. So we said that if so, let's say our reaction was, this is we I'll extend it. Let me extend this. I don't want to start saying things that are confusing to people, right? So we had for example, let's say we had our example above. Let's go back to our example here above. And I'm kind of going over the place. I'm just trying to find an example of rate. So here's a rate equation here, right? K is equal to AB. That's the rate equation, right? That would mean that both A and B are part of the rate determining step. We don't consider anything that's not part of the rate determining step. Because the only part, as you already said, the rate determining step is what determines what's in our our rate determining step determines the rate of our reaction because it's the slowest reaction because it has a high activation energy. Anything that's not part of the rate determining step, so those reactions have low energy, they're not going to be part of the rate determining step, and therefore they're not going to be part of a rate equation. So that can be read either way. Anything that's part of the rate determining step will be part of the rate equation, and therefore anything that's in the rate equation is in the rate determining step. All right, and the reasons why this is so important to us is because any reactant appearing in the rate equation is involved in the rate determining step, and if two reactants appear in a rate equation, we know that they're both involved in the rate determining step, and this means the mechanism must involve them colliding at some point. So we know definitely those reactants are the ones that are most involved in the collisions of the reaction. Obviously there are the collisions as well, but the ones that we're focusing on are in the rate determining step. All right, so if I was to go here and I asked you guys, right, how would you write a rate equation for this reaction? If I was told you to write a rate equation for this reaction, so notice it, yeah, if I told you to write a rate equation for this reaction, pause the video now and try and write it out for this one here, that example that I had here. All right, so I hope you try to do it. How I would write that one is R is equal to K by alpha beta. Because I've just made it very clear already that it's only alpha and beta that are in the rate determining step here, right? I know probably you probably got confused between, I should have had like probably a better way of showing you alpha plus something and beta plus something, but these are the two, I mean, I've used beta as like points on, that probably wasn't a good example because I've used beta as points on the graph to show this point here and that's the one point there. I meant to say that alpha and beta are reactants, but that's probably, I apologize on that one. That one probably wasn't the best example. I should have made it clear what's the difference, what's here. I should have made it clear what's going on here. Yeah, I meant to say that alpha plus beta is going on here. That's what I meant to say. Alpha and beta just stops. They're just points on the graph. Alpha plus beta was this here. All right. I apologize for that. But the point being I'm trying to say here is that we wouldn't talk about anything to do with A. We wouldn't consider anything to do here. This would have been A plus alpha. We're not considering that. We're not considering beta plus B. B isn't part of our rate determining step. A isn't part of rate determining step. Only alpha and I mean that just I'm really messing this up. I'm really sorry guys. I'm not really making the best examples here. I'm not making the best examples here. Because technically it's anything from here to get to alpha. Right? So what I meant to say was A reacting with something, let's call it plus C, to form alpha is what I meant to say. Alpha plus beta, and that forms, well, alpha plus something goes to form beta. Beta plus something goes to form B. I haven't found the best example here. You know what? I should try that example again. Let me try it. Let me go and try again. Right? I apologize for that one. That probably wasn't the best example. Let me go for a better example because I think people got what I was trying to say here. My point was trying to mean that this is the rate determining step here. But I'll produce a better example for you. Yeah. I've got a perfect example here. Good. Yeah. All right, okay, cool. I know exactly what I want to do now. All right. I do apologize. I should have done this when I was actually planning out this video. But you guys know me. You know me. All right. The other example wasn't a good example. I have examples here. So this is a multi-step reaction to go from product one to product four. What would if I told you guys to write out the rate equation for this multi-step reaction, how would you do it? That's what I would say. How would you go about doing this multi-step reaction? So how would you go about making a rate equation from this reaction, right? Pause the video now and try and do it. All right. If you haven't paused the video and you just looked and said, I have no idea what he's talking about, I do apologize again because I did to make this on the spot, but hopefully this would be a better example than the last one. The rate equation for this would be R is equal to K A B. And that's it. Because I put the activations here underneath. So this is high activation energy, this is low activation energy, this is low activation energy. This one here has the highest activation energy, and therefore it has the it's the slowest step out of all of the three reactions. Therefore, the rate of this reaction is determined by this first step from 1 to 2, and therefore that is the rate determining step. And that's the reaction that's going to form a rate equation. We don't care about C to D, C plus D or E plus F because they're not part of our rate determining step. Only A and B are part of that rate determining step. And that's how we draw our rate equation. R is equal to K times by A times by B. Now let's say it was this, right? Let's say I change this to 2B. Try and write out the rate equation now. All right. You should probably just be able to know that if you're well comfortable with rate equations, you know it's be that R is equal to K times by A B squared. Now, when you're talking about rate equations, you have a number in front of you, or a number value or a molar value in front of your B. It means that in our rate determining step, 1 mole of A is colliding with 2 moles of B, or 2 particles of B are reacting with. So if we're talking about in particles, right? For every particle of A that collides, there's 2 particles of B that would collide, right? And therefore, in a reaction, we actually would square that compound that has in this case, if we have 2, that number that's part of a molar value becomes an exponent, and that's our order. So the order of B is 2, right? So it's B squared. If it was 3B, it would be B cubed. 4B, B to the power 4. I think you get my point, right? But it's K, in this case, would be the rate equation would be R is equal to K A B squared. Specifically B squared. It's not A B squared, it's A times by B squared. All right. Hopefully I didn't make too much of a mess of this. This part here is the biggest part I wanted you to get across, because this I admit I probably should have planned this out better, but I can do an exam question that I'll show you I guess in a later video, in another video, but I've got one example here for you today. But this part here, understanding what the rate determining step is and how that's related to a rate equation, was the point I wanted you to get across the most. All right, so reactant order. So if a reactant appears in the rate equation, it will have an order, and if the order is 1, then one molecule of the reactant is involved in the rate determining step. If the order is 2, then 2 molecules are involved. And as I just kind of already told you, this gives us more information about which molecules and how many of them are colliding at some point in the mechanism. Reaction. So for, let's say we're going to use an example here for a nucleophile and a halogen alkane. There are two possible mechanisms for the reaction between a nucleophile, say a hydroxide, and an halogen alkane, say 2-bromo 2-methylbutane. You can have a one-step process where the nucleophile collides with the halogen alkane and injects the bromide ion. You could also have a two-step process where the bromide leaves first and then the nucleophile adds. So for this reaction, it's found the rate equation is R is equal to K times by CH3, well, R is equal to K by 2-bromo 2-methylbutane. What this implies is that the nucleophile is not involved in the rate determining step, i.e. the order of hydroxide ions is 0. And if the order of hydroxide ions in the rate determining step is 0, it means it's not part of it, but as I said, anything to the power of 0 is 1, right? We wouldn't call this times, we wouldn't write times 1 in anything. It's just, you just don't include it, right? It means that if this is multi-step, this is it. Say this is a multi-step reaction, where the bromide leaves first due to the nucleophile being added. It means that the actual part of the reaction, the actual rate of the actual mechanism that determines, or the step in the mechanism that determines the rate of this reaction doesn't involve the hydroxide ion, and therefore we don't need to. It doesn't matter how much hydroxide ions it doesn't matter how much. It doesn't matter by how much we increase the concentration or decrease the concentration of hydroxide ions. It would have no effect on the rate of our reaction because it's not involved in the rate determining step. And that's all it means. So if you find that an example like this is, so I'm going to bring it back to this here, right? It means that for this reaction here, to getting from getting to 1, what does it say? From getting from 1 to 4, if I wanted to increase the rate of the reaction, I would increase or decrease. If I wanted just to change the rate of this reaction from going from 1 to 4, I would increase or decrease the concentration of A or B. I could increase the concentration of C, D, E, and F as much as I want, but it wouldn't affect the rate of our reaction at all. Zero effect, because this would have 0 order, as this is not part, because they have no, so they're not part of the rate determining step. So they would have no effect on our rate of our reaction, because they have 0 order in terms of the reaction, in terms of our rate equation. So they would not have any effect. If we halve the concentration of A, that would almost half the rate of our reaction. We have B squared here, so I mean, I'm not going to get too much into the maths of it, but ideally decreasing the rate of, or the concentration of A would definitely decrease the rate of our reaction here, and decreasing the concentration of B would definitely decrease the rate of our reaction for B as well. I mean, probably B more strongly because this is squared, there's 2 of them, but the point being that only affecting the concentrations of A and B will affect the rate of this reaction. Right, so now I've got an exam question here. It's 11 minutes. I want you to try and answer it. Yeah, that's what I'm going to do. I want you to just try and answer this this question I'm going to show you here. So I'm going to just show you all the questions so that you can see all of them. Right, and that's 11 minutes. I want you to pause the video now and try and answer those questions. All right, I'm assuming that you've unpaused the video now, you've tried to answer them. I will now go ahead and try and answer them myself. So, as I said, I just picked this one out because I think it looked like the correct one. It's not a too difficult one, but I think it's one that you can do. I'll probably go into more harder examples when I get to the point of when I finish all of physical chemistry. Anyway, 11 minutes, 3, 2, 1, go. All right, the rate of hydrolysis of an ester, temperature, oh, just name the ester. 1, 2, 3. This is the alcohol, so that's propyl methanoate. Using X to represent the ester, write a rate equation for the hydrolysis of reactions. So they said we can use X to represent the ester. First order with respect to ester and first order with respect to hydroxide. And so R is equal to K X OH minus. When the initial concentration of X was 0.024 moles per dm cubed, the initial concentration of hydroxide was 0.035 moles per dm cubed. The initial rate of reaction was that. Calculate the value for the rate constant at this temperature and give us, so just find K. So K is equal to R over X by, so rearrange the equation. R is equal to, so K is equal to X, K is equal to R over X by OH minus. X is the ester that they have here. Therefore, K is equal to, they told us the rate of reaction was 8.5. This is just simple maths, just simple rearranging of the equation to find out the value of K. X was 0.024 and hydroxide was 0.035. Put that into a calculator. What is it? Now I've got to be careful. They've given us two significant figures here in our question, so I'll use two significant figures in my answer. So 0.10 times, no, that's it. And the units, very important they have units, that's where the extra mark comes from. Moles per dm cubed, moles per dm cubed. So just moles. I've cancelled out the moles per dm cubed on the numerator and the denominator, right? Moles per dm cubed here per second. And then I'm only doing this, I already know how to do it, I'm just doing it for the sake of you guys, so you can see what I'm talking about. Moles per dm cubed. Cancel out that, we'll leave the second to there. Moles minus 1 dm cubed per second. In the second experiment at the same temperature, water was added. So the original mixture, so the total volume was doubled. Calculate the initial rate of the reaction of this second experiment. So if you increase the volume by 2, so if you're increasing the volume, we're actually decreasing the concentration in our solution, right? Because concentration is equal to moles over the volume. If the moles of our compound stay the same, by moles, the number of molecules of our compound in the solution stay the same, but we've doubled V. So if that just stays as 1, but it's over 2, we've actually halved our concentration here. So that's what we're doing here with this expression, with our concentration here. So what we actually have to do is calculate the initial rate of reaction. R is equal to 0.1. It's only a 1 mark question, so I'm not going to go too much into writing the equation for it. 0.1 by 0.5 by, you don't have to write this down, you can just write down the answer straight away, but I'm just doing it here because it makes a bit more sense for me. That's mad. Man said Jesse Marsh already got sacked. That's tapped. Anyway, so 0.1, and just put that into a calculator, and you should be fine. If you just want the answer to these questions, you're completely free to just go and skip me talking over them. I'm only doing this for people that don't know how to answer these questions. If you just need a bit of support for yourself, you should have got 2.1 times 10 to the power minus 5. That's what I got. 2.1 times 10 to the power minus 5. They don't care about you having the moles per dm cubed per second, just in case. In the third experiment, at the same temperature, concentration X was half that was used in experiment in part A, and concentration of hydroxide was 3 times the original value. Calculate the initial rate of reaction in the third experiment. So it's still half, so X is still half, but the hydroxide ions has tripled. So R is equal to 0.1 by 0.5, times by 0.024 multiplied by 3 by 0.035. That's it. R is equal to. I actually can leave this at the same thing as my calculator, but just times that by 3. And I got here 1.26 times 10 to the power of minus 4. I'm just thinking to myself, how many they gave us. I think they may allow that, but I will round it to 3 significant figures. 1.3 times 10 to the power of minus 4. Because they did leave it in 2 significant figures, sorry. State the effect, if any, on the value of the rate constant K when the temperature is lowered, but all other conditions are kept the same. Explain your answer. I'd say if the temperature is lowered, it's lowered. There's a lowered rate constant because it's temperature dependent. So less particles, I'd say. Less particles have the activation energy. No, have energy greater than the activation energy. Is the way I'd put it down. Yeah, that's how I put it down. 3 minutes, 14 seconds left. I have more than enough time. Compound A reacts with compound B as shown in the overall equation. The rate equation for the reaction is so and so there. To deduce which one of the 3 stops is the rate determining step. Or it's clear to see it's clearly 2. For the reasons I had here, or step 2, I should say. The rate determining step is clearly step 2 because there's 1 mole of A and 2 moles of B in the reactant. These are the easiest ones to do. And I still had, even with me talking, I still had 2 minutes and 21 seconds left. So this is the easiest one here because you can clearly see the equation, the overall equation is A plus 3B goes from AB cubed, but it's only in the rate determining step, the factor affects the step that has the highest activation energy, or in this case the rate determining step is only 1 mole of A and 2 moles of B, because it's AB squared, which means in reality it's this, right? Of some form, something like that. So we're looking for something that has 1 mole of A in the reactants. It's all about the reactants. 1 mole of A in the reactants and 2 moles of B in the 1 mole of A and 2 moles of B in the reactants. Here is 1 mole of A, 1 mole of B. No. 1 mole of A but 3 moles of B. So no. This has 1 mole of A and 2 moles of B. So that's definitely part of our rate. That's definitely part of our rate determining step, and therefore that is that's the rate determining step, and that's the explanation why. Because there's 1 mole of A and 2 moles of B in the reactants. Do I have the? Please tell me I have the. Nope. Do I have to go here? Right. What question that? Question 3. So propyl methanoate, yes. KXOH minus, yes. 0.10, yes, 2 significant figures minimum. moles to -1 dm³ per second, yes. And obviously doing this equation here was getting you a mark, doing the conversion 8.5 times 10 to the power -5. This one here, 2.1 is enough, times 10 to the power -5, yes. It's only one marker there. Next one is also one marker. 1.3 times 10 to the power -4. I'm happy that I simplified that. And if you're doing this and you didn't do a box around it, draw a box around it, because otherwise your examiner might get confused between the two answers. You're showing that it is 1.26 times 10 to the power -4, but you've rounded it down to 1.3 times 10 to the power of -4. Even says, it says allow anyway, even though they'll still allow you, but don't risk it. It says anything between 1.26 and times 10 to the power -4 to 1.3 times 10 to the power -4. All right. But I just say, just, it's two significant figures, so do two significant figures. Lowered, so load rate constant. Few particles have collision, have energy greater than activity. So less particles have I should have said less particles collide. So that's one thing I could have probably said better there. I know I'll probably get the mark for that, but I want to be I'll be critical of myself here. So 1 mark here. Less particles have yes. Sorry, I know that's probably not clear to see. I meant to say less particles have energy greater than the activation energy. That's terrible handwriting. Good. And then the last one was step 2, 1:2 mole ratio, or involves involves 1 mole molecule particle of A and 2 moles of B. All right, that's it. Hopefully this video was helpful, and I will leave it there.